Hi guys, welcome to another calculus class. We're going to talk today about continuity. So continuity, it's a new concept to you in calculus, although it's not um, really all that new. An idea, it's just we're going to formalize it a little better. Okay, so a function is continuous at a point C if these three conditions are met. So we're going to look at those three conditions. Okay, the first one, well, the function has to exist at a point. Okay, a function has to exist at that point. Two, the limit has to exist at that point. All right, and then number three, the limit has to equal the function. I wish I could type that because man, that handwriting looks terrible. But anyway, those are the three things that have to occur, and I'm going to try to look at a few functions that will help us out with this and get this idea. All right, so let's take away this floor function for right now. So let's look at a function. Um, oh, that's not what I wanted. Y equals x squared plus 1, or 2 for that matter. Okay, now you'll notice that I could draw this graph without ever picking up my pencil. This graph will be continuous everywhere. But let's take the point right here. That would be the point 2, 6. Let's take this point. Okay, the first thing, does the value exist? Does the function value exist? Well, yeah, we can see it right here. Okay. The second thing, does the limit exist? Well, you can see if we trace along the graph here. So if I trace along the graph here and I trace along the graph here, they both intersect at that same point right there. So yeah, the limit exists. And then the third thing, does the limit equal the function? Notice that 1 has to equal 2. Well, yeah, it does. The limit comes to 6, and the limit comes to 6 there. All right, we'll look at some examples in class to try to look at some of those other things, but let me see if I can give you a quick example here that we can see. So let's do this one, x minus 1 over x squared minus 1. Okay. And so here's a nice hyperbola. And hopefully you recognize that at 1, there it is, it's undefined. And it has an asymptote here at x equals negative 1. Let's make this x equals negative 1, and you can see that asymptote then. Okay, so there's that asymptote. Okay, so is it continuous here at 1? Well, if I were to draw this, I would have to skip over that. So I'd have to pick up my pencil. Anytime. So when drawing a graph, if I had to pick up my pencil, the graph is not continuous at that point. Now, let's make that a little smaller so you can see all of that. Okay, so that's not a very mathematical definition, but hopefully that idea makes sense. So here at 1, I would have to pick up my pencil. Okay, everywhere else I could draw, except here at negative 1. I'd also have to pick it up. Well, why does that not work? It also doesn't work because f of c doesn't exist. So those are both cases where f of c does not exist, and it's not continuous at that point. Everywhere else, it exhibits continuity. Okay, these other two conditions are not as easy to identify. They're not going to, you're probably not going to see them on functions that we actually see this here. Okay, so that's the idea of continuity. Let's look at 1 over x here, which you'll kind of see the same thing, 1 over x. There's that hyperbola. it has the asymptote there. So what would we say here? We would say this is continuous everywhere except for x equals 0. Okay, that would be the best answer for that one. That's how we discuss the continuity. Now, this one is a little bit tricky. So I think that's the correct one. 3x minus 2. Okay. Now, here I have to start. Okay, I have to pick up my pencil and move it to this point right here, and then I could draw. Now, it depends on the textbook, but some textbooks say it's not continuous at this point right here. This textbook will argue that it is. I will talk about that in class, but I just want you to be aware that some textbooks say it's not continuous here because the limit doesn't exist. There's nothing from the left. Okay, but this textbook argues that it is continuous because it's just one single solid line, not a line, a curve. Okay. Like I said, we'll talk about that in class. So what this book will say, it is continuous everywhere. Let me see if I can spell this correctly. On its domain. So continuous everywhere on its domain. That's this book. Okay. All right. Oh boy, here we go. So some properties of continuity, and they're not terribly important, but it is kind of important that we know these things. So if I have a continuous function f, if I multiply it by a constant, it's still going to be that way. So let's look at let's go back to 1 over x. 1 over x. How about that? Okay, if I multiply this by 2, it's still continuous at all the same values. I multiply it by 54. It's still continuous at all the same values, although harder to see. It still has this asymptote at 0. Okay, if I add 2 functions or I subtract 2 functions, still continuous. If I multiply 2 functions, still continuous. This one is a number I multiplied by. This is 2 functions that are continuous. Okay, and then f divided by g. Now, this has a little caveat. If g is equal to 0 at the point C, then it can't happen. Then it's not continuous there.